Hello friends, in this lecture we are going to discuss construction of green function and its application in converting linear differential equation into integral equation, and in some condition we are able to solve completely the given differential equation. So let us start. So before going to start with the actual construction of Green's function, we first discuss some basic thing about adjoint operator. So for adjoint operator, the idea is that let we have L be the differential operator, L which is defined as ax d2 dx square plus bx dy dx plus cx, and here this u and v are considered as, say, some completely arbitrary. Only the requirement here is that this LU and L star V exist. Okay. Now here we are considering this particular example. So here if you look at, we are just multiplying V and integrating with respect to, say, some interval a to b, where a and b are some interval where we want to perform this operation. If you look at here, this is done, so integration by part we have done once. So here if you look at this VA u double dash and integrate by part, we will get this VA u dash, and if we plus a to b minus VA dash u dash, and if you perform integration by part on this VB u dash, we will get this VB u and minus integration of a to b VB dash u. So if we do it, all this calculation, we will get this. So this is the boundary condition evaluated at the boundary point a to b, and this is the integral. Here we have seen that corresponding to differential operator L, we have defined adjoint operator defined as this L star given as this AV double dash minus BV dash plus C of V, and if we expand this expression, we are going to have this thing, equation number 4, that a v double dash plus 2a dash minus b v dash plus a double dash minus b dash plus c. Now here in the case when this L star is the same as L, we call this operator as self-adjoint operator. So what it means that, let us say that L of u is defined as a u double dash plus b u dash plus c u, and calculation we have this L star v as a v double dash minus b v dash plus c v, and if you simplify this, you will get a v double dash plus 2a dash minus b v plus c of v. Now if you say that this L star is same as L, this implies that this implies that L star operating on u is same as L of u. This implies that your coefficient of u double dash is basically, if we compare this with this, you say that a is equal to a. So this is the coefficient of u double dash, and if you look at the coefficient of u dash, then it is basically, here we have 2a dash minus b, and here we have, say, b, and if you look at coefficient of u, then here we have there is a problem here. Here it is a double dash minus b dash plus c. So here if you look at the coefficient of u, we have a double dash minus b dash plus c, which is given as c here, and if you look at, if you solve this, then here we get what? Here we get that a dash is equal to b. If you use this condition a dash equal to b, then this is nothing but a double dash minus b dash is simply going to be 0. So this implies that c equal to c. So it means that when we assume a dash equal to b, then this is trivially true. So it means that in the case of when we have L star is equal to L, or we can say that we have a self adjoint operator, then we can write our LU as this, that AU double dash plus, now B is your A dash, so it is A dash U plus C of U dash. So here I can rewrite this as d of dx of A U dash plus C of U. So this is this form of operator L is known as self adjoint form. So we say that here L is the self adjoint form, adjoint operator. We don't say D, we say that L is a self adjoint operator, defined as this. Now this we have seen that when B equal to A dash, then we call this L operator as self adjoint operator, and in this particular case your L can be written as d by dx of A dx plus C. Now let us come to construction of green function. So we to initiate, we take an example of one boundary value problem given as u double dash x plus phi of x with the boundary condition that u0 equal to 0 and u1 equal to 0, where phi x is some given function. Now here we may consider ux as, say, static deflection of the string, and this string is stretched under unit tension between fixed endpoints, and here we are putting this phi x as a force distribution under unit length. Here we can draw it like this. So here we have x equal to 0, and here we say that x equal to 1, and between this two fixed end we have a string attached here, and we have a force, say phi of x, right, force distribution, and it is acting on this string, and here we have a, this is unit length. Okay, so now we try to find out the solution of this particular problem, u double dash x equal to phi x, u0 equal to u1 equal to 0. So we may try to find out the solution using variation of parameter method, but here we try to solve it in a different context. So here we try to solve this using Green's function method. So if you look at the idea is something like this. Here we have this L of u, which may define as u double dash. Is that okay? And when we define LU as u double dash, then this problem is given as L of u is equal to phi, with the condition that u of 0 equal to 0 equal to u of n. And we try to find out the solution of this non-homogeneous linear ordinary differential equation. So what we try to do is we try to operate another operator, say L star, I am just denoting it by L star, which we operate on this. So we will get what? So we can write it like this. So L star operating on LU is same as writing L star phi. Now what we try to do is we try to define, we need to find out this L star in a way such that L star L is going to be identity, or I can say that this L star is going to be right inverse to this L. So we write it like this. So here we simply say that u is going to be L star phi, right? Now since this L is defined as a differential operator, then we can consider, we may consider that L star is going to be an integral operator. So when we operate L star phi, L star on this phi, we may write it like 0 to 1 some g xi x operating on phi of xi d of xi, right? So here we say that this L star is L star phi is given as this integral thing. Now here I can say that this g xi x is a kernel of this L star, and we call this g xi x as kernel of L star and commonly known as Green's function. Okay. So it means that if we can find out this Green function, then we may find out our solution ux given as this. So here we can write ux as 0 to 1 g xi x phi of xi d of xi. So our aim is to find out this Green function. So how to do it? So for that use this relation which is known as Green's formula. So if you look at, you remember this, the process of finding adjoint operator. What we have done here, we have v of Lu dx, and we have written it some boundary terms between a to b if the limit is a to b, plus here we have a to b and we have u L star v d of x. Now here in this particular case your a is 0 and b is equal to 1. So what we try to do is we try to look at the same formula, but now we simply say that v is replaced by this Green's function g. So here we have seen that while defining the adjoint operator, we have this relation that a to b v Lu dx equal to boundary terms plus a to b u L star v dx. For this particular problem we have a equal to 0 and b equal to 1. What we try to do is we just replace our v by Green function g and try to solve this. So here we have 0 to 1 g Lu d xi equal to boundary term between 0 to 1 and plus 0 to 1 u L star g d xi. For this particular problem we have L as d2 by d2 d xi square, and if you simplify this, what you will get here. So here we have 0 to 1 v, which is replaced by g now. So g L u dx is equal to, I am writing here 0 to 1 g and L is u xi d xi. I am denoting here that variable is xi here. So this I can write it as first integration of second. So u xi 0 to 1 minus 0 to 1 g xi u xi d xi. If we perform one more time integration by part, you will get g u xi 0 to 1 minus, here if you do g xi u between 0 to 1 minus 0 to 1 g xi u d xi. If you simplify this, you will get g u xi minus g xi u evaluated between 0 to 1 plus 0 to 1 g xi u d xi. So it is written like this. So here if we write down the boundary points here, then we have g 0 to 1 g xi x phi xi d xi equal to g 1x u star 1 minus u1 g xi 1x minus g 0 x u dash 0 plus u0 g xi 0x plus 0 to 1 u xi L star g d xi. So here if you remember, we have u double dash is given by phi. So I am writing here phi in place of u double dash xi. So if you look at here, then if we look at the boundary condition is that u1 is equal to 0 and u0 is going to be 0. So it means that these two term is going to drop out. The only thing left here is this and this, and if you look at this term, I want that this should give the solution of the problem. So it means that u 0 to 1 u xi L star g d xi should somehow give the function u of x here. So to show that this will give you u of x, here we assume that our green function L star g is given by g xi x here, because here we are dealing with self adjoint operator. So L star is nothing but same as L, which is double derivative with respect to xi here. So g xi equal to delta xi minus x, and the boundary condition, just to make these two term vanish, that g1x and g0x we are assuming that it is 0. So this is an additional condition we are putting here, that g green function should satisfy this ordinary second order ordinary differential equation plus g0x equal to g1x given as 0. If we use this, then this term, last term, this 0 to 1 u xi, now this is what, delta xi minus x. So here delta is your Dirac delta function, 0 to 1 g xi x phi xi d xi equal to g1 x u of 1 u dash 1 minus u1 g xi 1x minus z0x u dash 0 plus u of 0 z xi 0x plus 0 to 1 u xi L star, which is same as L here, g d xi. Now since we already have u0 equal to 0 and u1 equal to 0, so if we use this condition is simply 0 and this is again going to be 0, right. So now if we want that this will give us the solution here, what we want is that we choose our g in a way such that this will give you u of x and g1 x should be 0, so that no boundary term will be there, and g0 x is equal to 0. So here what we want is this we can achieve by saying that if L star g, which is same as L g here, so it is g xi here, and we want that this should be given as delta xi minus x. So if we assume this, then 0 to 1 u xi delta xi minus x d xi is going to be u of x. So here this is the filtering property we are assuming here, that 0 to 1 delta x minus a f of a d of f of x d of x is going to be f of a. So here we are using the filtering property of Dirac delta function. So it means that if we assume our green function will satisfy this equation, that g xi equal to delta xi minus x and satisfying these two boundary condition, that g1 x equal to 0 and g0 x equal to 0, then this will also vanish and this is coming out to be u of x. So it is coming out to be u of x, and we can rewrite this as u of x is equal to 0 to 1 g xi x phi of xi d xi. So this is our solution, provided we should know what is g of xi x. So let us try to find out g xi x with the this boundary value problem here and try to find out what is g xi xi. Okay, so for that here just look at here these are the Green's function satisfy these boundary conditions. So L star g equal to g xi xi equal to delta xi minus x with the boundary condition, and solution is given this. Okay, now if we look at this boundary condition, your g xi xi is equal to delta xi minus x. So we integrate with respect to xi, keeping x as fixed variable. So we are integrating this g xi xi equal to xi delta xi minus x. So here we integrate with respect to xi, keeping x as fixed. So g xi 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 x d xi between 0 to 1 is equal to 0 to 1 delta xi minus x and d xi. And if we recall here that this Dirac delta function delta xi can be considered as derivative of Heaviside function. So what is Heaviside function here? Here Heaviside function is defined as 1 when xi is positive and 0 when xi is less than 0. So we can, this is available in any of the standard textbook of differential equation, that delta xi is defined as S xi, where Si is a Heaviside function given defined as this. There is a small hint for this particular problem. So I can write this delta xi as limit, say epsilon tending to 0. I can write it here as minus epsilon h minus epsilon minus h epsilon h epsilon minus h minus epsilon divided by 2 epsilon, right. So here xi minus epsilon and xi plus epsilon minus xi minus epsilon by 2 epsilon. So you can take this delta xi as derivative of this. So using this concept we can write this as h of xi minus x plus some constant a. Now so this is nothing but g xi x is given by this. I am not putting the limit here 0 and 1, we simply integrating in a definite, as a definite integration. So that is why I am putting this integration constant a. So now we want to find out g xi only. So integrate one more time. So we have g xi x given as integration of h xi minus x d xi plus a xi plus b. So this you can get this as xi minus x h xi minus x plus a of xi plus b. So I can write it g of xi x is this. So here I am using this integration, that h of xi minus x d xi is given as xi minus x h of xi minus x. So this you can prove as a simple exercise of Heaviside unit step function. So once we have g xi x given in this particular form, then using the definition of as xi minus x, I can write this as, say this will activate when this argument of h is going to be positive. So it means that when xi is greater than x, we have xi minus x plus a xi plus b, and when we have xi less than x, we have a xi plus b, right. So here we have to, how to find out this a and b. For that we have condition given to us that g of 0x is 0, g of 0x is 0 and g1x is equal to 0. So g1x equal to 0. So if we operate, if we use these two boundary condition, then we can find out a and b. How we can find out? Let us see. Let me write it here. This. Then put g0x equal to 0. Then here when we put xi as 0, then this is going to be a negative, then this will be a 0, and you can simply write it here as 0 times sorry, this I can write it here a into 0 plus b. Similarly g1x, it is 0 here, then we can write 1 minus x and this h1 minus x here plus a into 1 plus b. Now look at here this h1 minus x, whether it is positive or not. So if you look, remember your problem is basically this, u double dash x equal to phi of x, and condition was a u0 equal to 0 equal to u1 here. So here your x is between 0 to 1. So it means that this 1 minus x is going to be positive. So if 1 minus x is going to be positive, then this is going to be 1. So I can write it here, this 1 minus x plus a plus b here. So and that is going to be 0. So this I can write it here as b equal to 0. This implies that b equal to 0, which is clear from this, and you can write here a as this x minus 1. So I can write it here that g xi x is defined as xi minus x h xi minus x plus x minus 1 xi. Now again using the formula definition of xi minus x, I can write this as xi minus x plus x minus 1 xi when xi is greater than x, and x minus 1 xi when xi is less than x. Or you can simplify this further, and it is what? This is simply xi x minus x. So xi x minus x when xi is greater than x, and x minus 1 xi when xi is less than x. So this I can further write in a different manner. So I can write xi minus 1 x when xi is greater than x, and x minus 1 xi when xi is less than x. So here our green function is coming out to be this. So if we remember, our solution is going to be written as u of x is equal to, in integral format, 0 to 1 g xi x phi xi d xi. So here where g xi x is defined above, we can say it is defined by this formula. So we can write it here, g xi x is equal to this. So we can call this as star. So define above by star. So it means that our solution of the problem is given by this. So we have seen that ux is given by 0 to 1 g xi x phi xi d xi, where g xi x is defined above by this. So here, So it means that I can write down the solution here. Once we know what is phi of xi here, then we can write down the solution in this particular integral equation, Fredholm integral equation. Now here we have a very interesting interpretation of g xi x. If you remember here in the beginning, we have started all this for solving this particular problem, u double dash x equal to phi of x and phi u of 0 equal to u of 1, and here we simply said that this ux is nothing but static deflection from the equilibrium position under the force phi of x. But when we calculated our g xi x, then it is what? It is basically L star g and we have delta xi minus x. Here L star is given as d2 by d xi square and g is nothing but g xi x. So it means that it is given as g xi comma x equal to delta xi minus x, and with the condition that g 0x is equal to 0 equal to g1x. So here if I look at the same interpretation for this particular problem, then I can consider as that g xi x is basically deflection at a point xi here when a unit force delta xi minus x is applied at the point xi equal to x. So it means I can I'm just repeating it one more time, we can consider that this g xi x is denoting the deflection in string when unit force is applied at xi equal to x. So I can write that when we apply g xi x phi xi d xi, then we can say this is the deflection in string for the force delta xi minus x phi xi d xi, right. So it means that I can consider that g xi x phi xi d xi is the deflection in string when you apply delta xi minus x phi xi d xi force at point xi equal to x. So this is the force we are acting at xi equal to x. Now this xi is a variable point. Right now we are considering only the fixed point xi equal to x. Now if we vary for every point between 0 to 1, we can say that this is the deflection, this will represent the deflection if this is the force acting on the string. So this will represent your u of x, and the force it is given as, if you apply your filtering property, then this is nothing but your phi of x. Is it okay? So it means that ux is going to be a deflection in your string if phi x is the force applying on the string per unit length. So that is the that maybe we can consider as a explanation for this g xi x. So here in today's lecture, in this lecture we have started the concept of Green's function and see that how we can solve a given ordinary differential equation with the help of integral equation, and if your function phi xi is known to us, then we can find out the complete solution. Thanks for this lecture, thanks for listening us, and in next lecture we will meet.